You know those weather maps, right? The ones with the smooth, flowing colors showing temperature? Or maybe a map of air quality across your city. Ever stop and wonder, how do they do that? They don't have a sensor on every single street corner. Well, today, we're going to pull back the curtain on exactly that. We're talking about how we fill in the gaps on a map using a really cool process called spatial interpolation.
All right, let's make this real. We're heading to Ghana. What you're looking at here is a map showing malaria prevalence. Now, each one of those red dots, that's a health clinic, a place where we have solid, hard data. We know exactly what the malaria rate is right there. But look at all that empty space. What about everywhere else? That's our problem. We've got a map full of holes. So here's the million-dollar question. How do you take just a handful of points and create a risk map for an entire country? How can you tell a village that's miles from the nearest clinic what their risk level is? This right here is the whole reason spatial interpolation exists. It's about turning scattered information into life-saving knowledge. So here's how we're going to tackle this. First, we'll talk about this map with holes. Then we'll get into the one simple rule that makes all of this possible. After that, we'll look at some simple ways to make a guess, and then a much, much smarter way. And finally, we'll put it all together to see how this stuff actually maps risk in the real world. Okay, so let's get a little more specific about our problem. Right now, what we have is what's called discrete point data. Think of it like a connect the dots puzzle, but we only have the dots. What we want, what we need, is the finished picture. A continuous surface where every single spot on the map has a value. We need to fill in all the space between the dots. So how do we even start? Well, what's so cool about this is that all the fancy math and complex models we're about to see, they all rest on one single, incredibly simple idea. It's a fundamental law of geography, and I bet you already get it, even if you've never heard it called that. And here it is. Everything is related to everything else, but near things are more related than distant things. That's it. That's Tobler's first law of geography. It's just a formal way of saying something you already know instinctively. The house next door is probably more like your house than one across town. This simple, powerful idea is the bedrock of everything we're doing. It's what gives us permission to even try to guess what's happening in those empty spaces. Now, if you want the fancy technical term for this, it's called spatial autocorrelation. All that means is that the data isn't just a random shotgun blast of points on a map. There's a structure to it. There's a pattern. And because of that pattern, because near things are more alike, we can actually make a pretty good, educated guess about the places we haven't measured. Okay, principle in hand, let's look at our first set of tools. These are the straightforward approaches, the ones that use pretty simple math to fill in the blanks. They're called deterministic methods. Think of them as our simple guess category. The word deterministic is key here. It basically means these methods are like a recipe. You put in your points, you follow the steps exactly, and you get an answer. There's no thinking involved. It's all about mathematical rules based on distance. It doesn't look for deeper patterns in the data, it just calculates. It's a solid first guess, but it's based purely on where your points are. Probably the most common and intuitive one is called inverse distance weighting, or IDW for short. So how's it work? Well, imagine you're in an empty spot on the map and you want to know your value. IDW tells you to look at your neighbors. The ones right next to you, their opinions matter a lot. The ones farther away, their opinions matter less. It's a weighted average where closeness is everything. Super simple, super fast. The only downside is that it can sometimes create these weird bullseye patterns right around your original data points. Then there's an even simpler method, Tixon polygons. This one is, well, it's ruthless. It just carves up the whole map into little territories. For every single one of our original data points, it draws a boundary around it and says, everything inside this little kingdom belongs to me. And every single location inside that polygon just gets the exact same value as the point in the middle. No averaging, no nothing. It's the ultimate winner-take-all approach, which gives you a very blocky-looking map. So those methods are okay. They get the job done, but they're a bit basic. They only care about one thing, distance. But what if we could do better? What if our guess could be based not just on how far away things are, but on the actual underlying statistical patterns in the data? Well, that's where we get into the smart guess. We're talking about geostatistical methods now. And this slide really gets to the heart of the difference. On one hand, you have the deterministic methods like IDW. They just follow a simple math rule based on distance. They give you an answer, but they don't tell you how good that answer is. On the other hand, you have geostatistical methods like kriging. These are the smart ones. They actually learn from your data. They figure out the spatial pattern first and then make a prediction. And this is the game changer. They also give you an uncertainty map. They literally tell you, hey, I'm really confident about my guess here, but over there, not so much. All right, time to meet the superstar of geostatistics, a method called kriging. Now, at its core, it's still doing a weighted average, just like IDW. But here's the magic trick. The weights it uses aren't just pulled from a simple closer is better rule. No, the weights are custom calculated based on a statistical model of your specific data. It's a tailored approach. And because of that, it can give you two things, a map of the predicted values and that all-important second map, the one that shows you just how certain or uncertain those predictions really are. So what's the engine driving this whole kriging thing? It's this chart right here, the semi-variogram. Okay, I know it looks a little intimidating, but the concept is actually pretty straightforward. This is basically a picture of Tobler's law for your data. Along the bottom, you have distance, and going up the side, you have how different the data points are. And look at the pattern. As the distance between points gets bigger, the difference between them also gets bigger, up to a point. It's a custom fit model of the spatial pattern in your data set. To really understand this, you just need to know three parts. See where the line hits the vertical axis right at the start? That's called the nugget. You can think of it as the built-in randomness or measurement error. Then, you see how the curve flattens out at the top? The height of that plateau is called the sill. That represents the total variation in your data. And finally, the range. That's the distance it takes for the curve to flatten out. It's basically the distance where points stop being related to each other. Past the range, a point is just too far away to tell you anything useful. Now, you're probably thinking, there's no way people do this by hand. And you are absolutely right. This is where powerful software comes in. We're talking about Geographic Information Systems, or GIS. Tools like ArcGIS have specialized extensions that do all this heavy lifting, building the semi-variogram, running the kriging calculations, and spitting out those beautiful, informative maps. Okay, enough with the theory. Let's bring this all back home. Let's go back to our problem in Ghana and see what happens when we unleash these powerful methods on real-world data. This is where it gets really exciting, because this is where the numbers on a screen can actually help save lives. And boom, just look at that. On the left is what we started with, a few scattered dots of information. And on the right, that's the result of kriging, a complete continuous map of malaria risk. All of a sudden, health officials can see everything. They can see the hotspots in red, the safer areas in green. They know exactly where to send resources, even to villages that were total blind spots before. It's a total game changer. And this isn't just about disease mapping. The same exact techniques can be used for all sorts of things. Here, for example, is a flood risk map for Accra. By taking data from specific points, maybe elevation or past flood levels, planners can create a map that clearly shows which parts of the city are in the most danger. This is how you turn raw data into a plan for protecting people and property. So after all that, what's the bottom line? It's this. There's no magic wand. There isn't one best method for every situation. The most important decision you make is choosing the right tool for the job. It all depends on your data, your goals, and what you're trying to say about the world. So how do you choose? Well, here's a simple way to think about it. The deterministic methods, like IDW, they're great for a quick look, a first draft. They're fast, they're easy, they give you a general idea. But kriging is for when you need to be right. It gives you a map that's statistically defensible, because it's not just giving you an answer, it's telling you how much you should trust that answer. And when lives or resources are on the line, that's everything. So, in the end, spatial interpolation isn't just a technical trick for filling in a map, it's a way of thinking. It's a powerful reminder that we can't always measure everything everywhere. It gives us the tools to peer into the blank spaces on the map and find the hidden patterns that connect everything. Which leaves you with a final thought. If we can't measure everywhere, what unseen patterns might be hiding in the spaces between the data we do have?